Hello there. Welcome to Astraveo's continuing education series, where for our podcast listeners we talk about mathematics, the physical sciences, of course the natural world, and our personal favourites, astronomy. Now, you know Joseph and I are all up in and about astronomy. We get super excited about that stuff. So let's get going. For today's episode of Astraveo's education series, we shall be focusing on kinetic energy and potential energy, specifically the potential energy in the Earth's gravitational field. Now, this was one of my favourite subjects in school. I absolutely loved it. I loved the demonstration of the interchange between kinetic energy and potential energy, and I'll show you what I mean by that shortly. So let's define a few things here. So kinetic energy is the energy a body has due to its motion. If a body moves, if something moves, it has kinetic energy. If it's like me right now, at rest, it's not moving, I'm stationary, my kinetic energy is zero. Now, potential energy is interesting. There's all kinds of different types of potential energy. One can have potential energy in a battery, so that's chemical. One can have the potential energy of the Earth's gravitational field. If I were to faint or fall asleep, I would fall over because I have Earth's gravitational potential energy in me. I could activate my chemical potential energy. I could move my muscles or my skeleton. That represents another form of kinetic energy, potential energy. So there are all kinds of different energies that we have in life, in the universe, in science. But today, like I said, we're going to concentrate on gravitational potential energy of the Earth and kinetic energy. So let's get started. So we've defined a couple of things already, but we've talked about kinetic and potential, but we need to explore those further because they sound like complicated terms. They're not really. Let's start with kinetic energy, okay? So, kinetic energy. Now, as the name might suggest, is to do with your kinetics, your energetics, your motion, and it has a formal definition. So, Ke, sorry, my pen's a bit squeaky, it is 1/2 times the mass of an object times its velocity squared. Now, this is really important. You can have lots and lots of kinetic energy if you either have a lot of mass or if you move really quickly. Now, you could be a blue whale. You could weigh a massive amount, 400, 500 tons. I'm not sure what the number is. It's a big, big number. But if that blue whale is not moving, its velocity is zero, it does not have kinetic energy. Very important distinction, that. Now, we should talk about something interesting here. There's a funny little thing in science, the difference between speed and velocity. You'll notice this as velocity, not speed. Now, speed is a scalar quantity. It's a number. It's just a size of a thing. I could walk at 10 miles per hour. Well, that's really quick. I could jog at 10 miles per hour. That is a speed. That is not my velocity. A velocity is a vector. Now, vectors have to have a direction. So I could say I can jog, my velocity could be I could jog at 10 miles per hour due north or due east. But if I say a velocity, I have to give a direction. That's really important in science. There's a big distinction. So be very careful with this one, please. Okay, so in scientific notation, mathematical notation, we can say mass is just m, kind of obvious, right? And velocity, I'm sure you're going to guess, is just v. Scientists and mathematicians, we're not always the most inventive. So 1/2 mv squared. That is the equation of kinetic energy. So it's written 1/2 mv squared. Now, in mathematics or science, if there's a dot here, it means multiplied. If there's no dot at all, but the characters are very close together, that also means multiplied. So kinetic energy is 1/2 mv squared. Okay, so I'm going to write this up here. We're going to keep that. It's really important. We're going to need to know that equation. 1/2 mv squared. There it is. So that's kinetic energy. Now, what about potential energy? That's also got a very formal definition. Now, I did tell you there are very different forms of potential energy. One can have chemical energy, like I said, in a battery. One can have mechanical energy. Imagine if I had a metal spring and I was strong enough to compress it, compress it, compress it. If I release my hands, what's going to happen to the spring? That's right, it's going to go boing. It's going to really spring apart. But we're talking today about the potential energy a body or a mass has in the Earth's gravitational field. So it has a very specific definition. Okay, so I'm going to write it out. Potential energy, with my squeaky pen as always, never fails. Now, it's the mass of an object times the gravitational acceleration in that gravitational field, and we'll talk about that in 1 second. I know it sounds complicated, but it's not really. Times the height of the object or body above the gravitational potential, in this case, the Earth. So as you might be able to guess, m is mass, like it was before. The character for gravitational acceleration is g. Told you physicists weren't that inventive. We're a bit straight-laced. We keep things simple. H, you might be able to guess, is height. So mgh, which is a little bit strange here in living near Boston, because I always think of that as Mass General Hospital, which is a famous hospital here in Boston, Massachusetts. But of course, for us as scientists, it's mass times the gravitational acceleration times height, mgh. Okay, now I did tell you I would tell you about the gravitational acceleration. This is a fundamental number. We can't change it. It's related to the mass of the Earth and, of course, gravity. So let's put it over here. It's a fundamental number. G equals 9.81, and it's an acceleration, so it has units of meters per second per second. Well, per second is written meters per second squared. We know divided by s will give us divided by s squared. And in mathematical notation, the divided by turns this 2 into a minus 2. So the units are ms minus 2. So this is what G is. Okay, so I'm going to get rid of this a little bit. I think actually sometimes the use of this is complicated and it makes people confused. So why don't we just leave it as meters per second squared? It's an acceleration, remember. So let's give ourselves a little bit of space again, but I'm going to keep writing this out so we don't forget. It's a fundamental equation. We're going to have the potential energy in the Earth's gravitational field is mass times the gravitational acceleration times h. Now, for those of you who know me well by now, taking equations and fundamentals and just leaving it like that, I don't really like that very much. Students, and me personally as a human, I don't like just sort of solid equations because they're really hard to imagine in my head. So when I was in school, which was, a couple of thousand years ago, we had a demonstration and it was beautiful. I understood kinetic energy and gravitational potential energy instantly from this. So I'm going to use the same demonstration that my teachers used on me way, way, way back when. And it's a very simple demonstration. I'll do it in red pen. So what we're going to do is we are going to say that this is the Earth, this straight line here. There you go, the Earth. And we're going to make as straight a cliff as I'm able to draw. I think you all know me well enough by now. I'm not the world's best drawer. And we're going to say that the height of this cliff, don't forget the height is important because the height parameter is in the potential energy equation. So this is height, H-E-I-G-H-T. It's hard to spell in English sometimes. Now I'm going to set this to 100 meters. And you'll see why later. It's going to make the mathematics easy for us. Now, right on the edge of this cliff, I'm going to put a little ball. Now, it could be a field hockey ball. I love field hockey. Could be a squash ball. I like squash too. I'm not so good at it now. The knees are giving out. I used to play soccer. It could be a soccer ball. Could be a basketball. Could be an ice hockey park. It could be anything. But let's call it a little ball. Could be a rock, I suppose. So let's put that ball right there, right on the edge of the cliff. It's stable at the moment. What is its kinetic energy right there? It's not moving, don't forget. That's right, its kinetic energy has to be zero because it has zero velocity. So I'm going to give this a KE equals to 0 joules. Now joules, that's the fundamental scientific unit for energy. You don't often hear about it in everyday life, but that's what scientists use to define energy. It's joules. Okay, it's 0 because the little rock or the ball is not moving. But it does have lots of potential energy because it's not on the Earth, it's above the Earth. It has a real height, which must mean it has potential energy. It has the potential to fall toward the Earth. We know that. If you've ever kicked a rock off the edge of a cliff, or you've thrown a ball from a playground or something, it takes an arc down toward the Earth. It has the potential to move. Now, again, we're going to make the mathematics easy. So I'm going to just say that this ball or rock weighs 1 kilogram. Now, depending on which country you live in, mass or weight isn't always measured in kilograms. Some people use pounds. So 1 kilogram is 2.2 pounds. But the standard scientific unit for weight, or mass more specifically, is kilograms. So we're going to express the weight of that object in kilograms. It's 1 kilogram. You'll see why. It makes the mathematics easy, actually. So it actually has bags and bags of potential energy. How can we calculate that? Well, we have an equation. We know its mass. We know the gravitational acceleration. We've already defined that over here, 9.81 meters per second. And we have a height. Therefore, we're able to work out that rock or that ball's potential energy. Let's do that. So, the potential energy of that object or ball, potential energy, PE equals mass times the gravitational acceleration times the height. Well, we know the mass in kilograms is 1. We know the gravitational acceleration is 9.81 meters per second, and we know the height is 100 meters. Well, 1 times 9.81 is obviously just 9.81, times by 100 is 981. 981. Don't forget the units, always important in science. So that object on the edge of the cliff has 981 joules of energy. So it wasn't 0, it actually has an awful lot. So I'm going to write it here. I need some space. Let's write it above. Well, no, that's a bit too tight. I don't really have much chance to be energetic here. So PE equals 100. That's the height. Didn't get that right, did I? 981 joules. All right. So what we can do now, I'm going to get rid of this, give myself some space again. You'll see why shortly. We can play the game of the ball or the rock on the edge of the cliff is at rest. It's not moving. 0 kinetic energy. Has bags and bags of potential energy, 981 joules. It's got the potential to fall down. There could be a gust of wind, an animal could have moved it, the rock could crumble, could be a tiny earthquake, something like that. This ball or rock has the potential to fall off the cliff. There it goes. So we might want to find out what velocity it's going to hit the Earth with. And there's an easy way we could do it. There's something in science called the conservation of energy. Energy can neither be created nor destroyed. So the total energy at the top, where the ball or rock is on the cliff, has to equal the total energy at the bottom when it hits the Earth. Now we have to do one thing. We have to ignore wind resistance, because the ball or rock will lose energy on the way down if we include wind resistance. And there's a little bit of complicated mathematics in there. Not terribly, but it does affect things. So we're going to pretend we're maybe on Mars, right? Where there's almost very little atmosphere. There'll be no wind resistance. For this, it's just a thought experiment. We're doing it to help us understand the relationship between kinetic energy and potential energy. So we're just imagining in our minds this is going on. So let's have that little rock or ball fall. It is going to end up right here. Well, we did say it was Earth. We're going to have to maybe pretend it's Mars. So, well, we can't do that, because if we pretend it's Mars, it's going to change the gravitational acceleration. Let's stay on Earth, but there's no wind resistance. Not quite scientific, but it proves a point. So our rock or ball is just about to hit the Earth's surface, 1 or 2 millimeters above, like this. So as it does that, the potential energy is going to drop to 0, because the height is going to be 0. The height above the Earth's surface will be 0 meters. So all the potential energy will be gone. Where will it be gone? Where will it go to? Well, that's right. It will be converted into kinetic energy, because the ball or rock will gain velocity. Conservation of energy, remember, you can't destroy the energy. It has to be transformed into another form. And the transformation goes from potential into kinetic. So here, lots and lots of potential energy, no kinetic energy. Down here, no potential energy, but lots and lots of kinetic energy. So down here, we can say that all the potential energy has been converted into kinetic energy. Now, we're going to assume it doesn't make a noise when it hits the ground, or it doesn't lose any heat, it doesn't just self-destruct, or it's going to explode. That would, of course, would then be other forms of energy. So again, we just have to play into the fact we're doing a little thought experiment here. So we know at the top the kinetic energy is 0, but the potential energy is 981 joules. Down here, assuming complete energy transformation from potential into kinetic, we can work out the velocity of that object just before it hits the Earth. And we can do it like this. Kinetic energy, as we know, is 1/2 mv squared. But we also know that the kinetic energy, if there's complete energy transformation, is 981 joules, as all that potential energy is transformed into kinetic energy. So we're going to write 981 equals, I'm going to do it this way, mv squared divided by 2. This effectively is 1/2. Dividing something by 2 is a half. And I'm going to, easy way to get rid of the 2 here, I'm going to times it by 2, because these will cancel. But don't forget, with an equation with an equal sign, anything you do to one side of the equation, you have to do to the other. So this has to be times 2. As I said, these will cancel, and you're going to end up with mv as 981 times 2. Well, sorry, mv squared. mv squared equals, not sure I can do this in my head at this time of night, but this is going to be something like 962. 2 times 9 is 1800. 2 times 80 is 160. 1960 plus 2 times 2 is 2. Yes. Don't forget, very important in science, the units. mv squared is 1962 joules, 1962. Okay, let's give ourselves a little bit of space yet again. Okay, I'm just going to turn it round to make it easier. I like going left to right. That's how I was brought up in the education system in Great Britain. So, and let's be formal. There's joules. That's the symbol for joules, J. Now, we know the mass of the object, right? We want to get rid of the mass of the object. But it sort of doesn't matter. The mass is 1 kilogram. So v squared times 1 is just v squared. 961 joules. Well, we know anything squared, a great way of getting rid of anything squared is to take the square root. Okay, so I'm going to take the square root. There's my funny little root symbol. We've seen this before in an earlier episode. The square root of anything squared is just the thing itself. So that will be v. Now, the square root of 961... Oh, let me have a think about this. 30, 40, 41, 42, 43, 44. It's about, I don't know the exact number, it's something like 44.2 or 44.3. It's about 44. Oh, whoops, I've been silly here. I've been very naughty. You didn't catch me out on that one. mv squared is units, is joules. But then when we transformed this, we took into account the mass. This is now, it's a velocity squared, so it's meters squared per second squared. Sorry, very, very bad, my fault. But we've taken the square root, so the units are meters per second. Now, the 44 squared exactly isn't 1961. It's about 44.2, 44.3. I'm not sure the exact number. So I'm going to show you a scientific notation here. 2 squiggles means approximately or about. So the velocity of the ball or the rock hitting the Earth is about 44 meters per second. Again, be very careful here because I've been doing science an awful long time, but I made that mistake from joules into a velocity squared because we took account of the mass. This is a kinetic energy. It hasn't got the factor 2, of course, because we got rid of that, but it's still in joules. It's an energy unit. But by taking out the mass, we have to go to meters per second, meters squared per second, meters squared per second squared. Okay, is that our final answer? No, you're quite right. What did we forget? Velocity is a vector. This is a speed. So this is not the final answer. I'm going to say downwards. We need a direction. It's a vector. We can't just say 44 meters per second. That would be a speed. A velocity has to have a direction. So we know that our ball or rock is ploughing into the earth at, I'll do it this way because I can't write upside down, 44 meters per second downwards. That's our velocity. So just from knowing a couple of simple things, we know that if we were to place a ball or a rock on a 100-meter high cliff, we're going to assume that the object is 1 kilogram or 2.2 pounds. If it falls off, or we give it a little nudge, or the wind blows it off, we can say with confidence the ball or the object, the rock, is going to hit the earth at approximately 44 meters per second straight down. So we've used our science, we've used our mathematical knowledge, we've understood that one can transform potential energy into kinetic energy. And that is a really powerful tool in science. Thanks for joining us.